Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So you can recall that in the last lecture I have given you the theoretical background on the Poisson probability mass function. Now the next question is how to implement those concepts in the R software. So that is what we are going to do in this lecture. And now I will suggest you one thing, that if you have not revised the lecture on the binomial distribution where I implemented that in R, then I will suggest you that if you can have a quick revision, then it will help you and me both in this lecture, because the same thing what I did there, similar type of things I am going to do here. So if you are happy, satisfied and confident with those things, this lecture will be can be understood very easily, right. So let us begin our lecture, and if you have not revised, please have a quick revision. Okay, so now we try to understand how we can implement the Poisson distribution concepts in R software. So just for a quick revision, you can recall that a discrete random variable x is said to follow a Poisson distribution with parameter lambda greater than 0. If its probability mass function is given by this probability of x equal to x, lambda is power of x exponential of minus lambda divided by factorial x, where the range of x is 0, 1, 2 and dot dot dot. And we also write this as x follows a Poisson distribution with parameter lambda, that x it tilde Poisson p inside parenthesis lambda. The mean and variance of this Poisson random variables are lambda and lambda e, so they are actually identical. Okay, so now in R, we will once again consider the same type of job what we did in the case of binomial distribution, that we would like to compute the density, CDF, quantiles and random numbers, right. So here the parameter lambda is now written as, say here, L A M B D A, all in lowercase alphabets lambda, and there is a command here dpois, POIS means it is coming from actually Poisson, and D means here density. So this command dpois gives the density, and if you want to write down, this is written as, say, inside the parenthesis x and then the value of the parameter lambda, right. And similarly, if you want to find out the CDF, you have to write here the command ppois, right. And then you have to write down here the data vector q, and then you have to write down here the value of the parameter lambda, and then you can use lower tail or lower dot tail is equal to true or false, exactly in the same way as we did in the case of binomial distribution. And then if you want to find out the quantile function, then you have to use the command qpois, QPOIS, and inside the parenthesis you can write down the value at which you want to find out the percentile, and then value of lambda, and then lower dot tail is equal to true or false. So this will give you the quantile function, which is the smallest integer x, such that probability that capital X greater than equal to small x is greater than or equal to p. And this command rpois inside parenthesis and lambda will generate say a small number of random observation from this Poisson distribution with parameter lambda, and if you try to use some invalid value of lambda, that will result in a NaN with a warning, right. So these are the things which I just explained you here, right, that x is the vector of non-negative integer, and then q is the vector of quantiles, p is the vector of probabilities, n is the number of random values to be returned, lambda is the vector of non-negative means, and lower tail, this is a logical operator which takes value true, that will compute the value of fx, and if it is false, then it will try to compute the value of probability x greater than x, which is 1 minus fx. Right. So now let us try to first understand how these probabilities will look like. So, what I try to do here, that I try to choose here a particular value of lambda, say lambda is equal to here 4, and then I try to choose the value of here x, say from 0 to 100, and which is controlled by here the variable k. And then I try to plot this function here as say plot x equal to k and y equal to prop. So, on the x axis we will have here the value of k equal to 0 to 100, and on the y axis we will have the value of the probabilities, which are the density values which are generated from the Poisson distribution for different values of k. And you can see here that this curve looks like this is the point, this is the point, and then it is trying to decrease, and after that it becomes here like this. So, this will give you an idea that how this curve will look like, or how these points will look like when they are plotted on the xy axis, right. And after this, this mean, this is going to give you the title of the curve and so on, right. So, now in case if you try to plot this curve on the R console, so you can see yourself here what is really happening. So, I simply try to copy and paste these commands on the R console. You can see here this will come out to be, I simply paste it, and you can see here this type of graphic will be obtained. And if you want to change here the value of lambda, you can simply change the value of lambda, and you can yourself observe that what really happens. So, this will give you an idea that how the this graphic look like for different values of lambda and for different values of here x, right. So, that is my idea that I wanted to inform you. Right now, I try to do the same example which I did in the last lecture, but I had obtained those probabilities using the theoretical concept. So, the first example that we did was that suppose a country experienced 4 earthquakes on an average per year, then the probability of suffering from only 2 earthquakes is obtained by the Poisson distribution, and we had obtained by like this probability that x equal to 2, that was obtained by this function. Now, I try to obtain the same value using the R command. So, now we want to compute the density. So, I have to use here the command dpoise, and I want to compute the probability at x equal to 2. So, this x equal to 2 will come here, x is equal to 2, and then whatever is the value of lambda, this I have to write down here, say LAMBDA is equal to 4, right. And then you will get this value, and you can compare, you are getting the same value that you got earlier. And alternatively, if you do not want to write here x or lambda, then you can simply write down here dpoise 2 and 4, but you have to be careful that the first position is occupied by x and the second position is occupied by lambda. These are the default position. If you interchange it, you will get a wrong answer, right. So, now we try to understand how one can find the quantile of this Poisson distribution from R. So, for that we have the command here qpoise, right. This calculates the quantile. For example, in the same example where we have taken lambda equal to 4, suppose we want to compute the 60% quantile. That is, we want to compute the value of k of q such that probability that x less than equal to q is greater than or equal to 0.6. So, this can be obtained by the command qpoise 0.6 and lambda equal to 4, and this will give here the value 4. And similarly, if you want to use here the option lower dot tail equal to true, that will also give you the same value here 4. One thing what you have to be a little bit cautious here, that when you are writing here q, then you have to simply write here 0.6. If you try to write down here q is equal to 0.6, then R will give you an error. Why this happened, I do not know, but that is the way it works, right. So, anyway, that is not a big deal. So, similarly, if you want to compute the probability of suffering 2 to 4 earthquakes in the same example that we just considered, that means we are interested in finding out the probability that x is lying between 2 and 4. So, you know from the rules of your cumulative distribution function that this can be written as probability that x less than equal to 4 minus probability x less than equal to 2, which is equal to here f4 minus f2, and now you know how to compute this f4 and f2. You simply have to write down here p poise q equal to 4 for here, and p poise q equal to 2 for here, and lambda will remain the 4, and then you can simply obtain this value, right. So, you can see here computing different types of probabilities is very simple when you are trying to do it in the R software. But now, let me try to first show you that whether you can obtain these values in the R software or not, right. So, if I try to say here this density at x equal to 2, I try to compute it in the R software, you can see here that density at x equal to 2 with lambda equal to 4 is coming out to be without any problem. And similarly, if you try to write down here this CDF at x equal to 2, you simply have to use here the command p poise, that will give you the value of the cumulative probability without any problem. And in case if you want to use the probability that x is greater than or equal to 2, that is also can be obtained without any problem, you can see here, right. And if you want to use here this option that you want to use the command lower dot tail is equal to false, you can see here that both these values are coming out to be the same. So, there is no issue, there should not be any confusion. And similarly, if you want to find out here the 60% quantile, this will come out to be here 4. And now, here I would like to show you that in the same command, if you try to write down here q is equal to 0.6, this gives a sort of error, right. So, do not worry. So, this is working. Now, we come back to our slides and try to take one more example, right. So, suppose there is an insurance company that handles 6 on an average number of claims means every day, right. Now, the question is what proportion of days have less than 3 claims, and what is the probability that there will be 4 claims in exactly 3 of the next 5 days, right. So, these types of questions are very popular in data sciences in real life. So, now we can assume that the number of claims on different days they are independent of each other. So, the company insures a large number of clients, and each having a probability of making a claim on any given day. So, that is pretty small actually, yeah. So, it is reasonable to suppose that the number of claims handled daily will be a Poisson random variable, and if this random variable is indicated by x, then the expected value of x is going to be 6, which is the value of lambda, right. Now, suppose if I want to find out that there will be fewer than 3 claims on any given day, that means I want to find out here the probability that x is less than or equal to 3, that is probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, or this is simply your here F3. So, I can compute this F3 using the command p poise for q equal to 3 and lambda is equal to 6, which will come out to be 0.15 approximately. So, you can see that computing the CDF and computing different types of probability is very easy, and since on any given day we will have fewer than 3 claims with probability only 0.151, very close to 15%, right. So, it follows that over the long run 15.1% of days will have fewer than 3 claims. So, you can see that computing these types of probabilities, CDF etc. is not difficult when you are trying to do it in the R software. Now, we try to see how the random numbers can be generated from this Poisson distribution. So, you know that the command for generating the random number here is R poise, and you have to give here n and the value of here lambda, and this will generate the small n number of random numbers from the Poisson with parameter lambda. Right. For example, if you want to generate 5 random numbers from Poisson distribution with lambda equal to 4, then we have to simply write down here R poise n equal to 5 and lambda is equal to 4. Definitely, when I am trying to show it on the R console, these numbers will not come, but something else will come, right. So, now let me just try to give you some idea that you are considering this type of event, and suppose you want to know that what will happen to the densities as this x is changing, right. So means how the probabilities are going to change. So because when you are trying to work in data sciences, you try to explore various types of aspects of the given experiment. So now I am assuming here that our experiment is now given to us, and that means the experiment is suppose conducted 100 times, and here the lambda is equal to 4, that we know, and we want to see how the densities change. So we try to make here a plot. So we try to take n equal to 100, lambda equal to 4, and we try to change the value of here this x by controlled by this here k from 0 to n. And so that means k takes the value here 0 to 100, and then we try to obtain the densities, and then we try to plot these densities with respect to k. So here in this curve you can see here we have here k, and here we have the densities. You can see here that at 0 the probability is nearly 0, and then it is increasing, and after some time this starts decreasing, and after that it becomes nearly the constant. So that means if you try to say here beyond say k equal to 13, 14, 15, like this number, the probabilities are nearly the same. So this is how you can extract some information about the process using this simple command from the R. And if you want to create the say this such a plot using the high density line, so you simply have to change the command, and you have to add here type is equal to h, and you will get here this type of command. So if you try to look different commands, different types of graphics, then it will give you different types of information, and based on which you are trying to will get different types of conclusion. So these are here the graphics that you have seen, and yeah, I will try to show you these things on the R consoles also, so that you get here more convinced. So you can see here that this probability is computed here like this, which is the same thing that you have just obtained. And now after this, if you try to compute this probability here, people, is that you can do very easily. I just want to show you here so that you are confident that whatever is written on the slide is also correct. Now in case if you try to generate here 5 random observations from the distribution lambda equal to 4, you can see here that these 5 numbers are 3, 3, 4, 6, 5, and if you try to repeat it, you will get here a different set of number, and if you again repeat it, you will get a different set of number. And if you try to obtain here suppose 50 observations, you can simply say n equal to 50, and you will get here 50 this value. So don't you think that this looks like as if you have repeated the experiment 50 times, right? So this is the advantage of the see here working on the software, right? And similarly, if you try to plot the curve or graphic which I have just shown you, you can see here this will come out to be like this, same graphic which I have shown you. And if you try to make here the type is equal to here h, you can see here now this graphic is changed to be like this. They are high density lines. Okay, so now let me come back to our slides and try to understand the next topic. So for example, under the same example, if you try to find out the mean and variance, the expected value of x will come out to be same as lambda, and variance will come out to be same as the lambda. So now just to have an idea about this process, that how this theoretical mean and theoretical variance are close to the values that are obtained in different experiments. So we try to generate here the n number of observations for different values of n from the same distribution with lambda equal to 4, and we try to compute their mean and variance, and we try to essentially simulate this probability model. And if you try to see here that in this case the expected value of x is 4, that is the mean is population mean is 4 and population variance is 4. Now if you try to get here 10 values, and if you try to find out their mean, this comes out to be 3.2 and the variance comes out to be 5.06. So you can see here these values are quite away from the true mean and true variance, and if you try to repeat it, means every time you will get a different value of mean and different value of here variance, right? That is obvious because there is a difference in different samples. Now in case if you try to increase the number of observation from say 10 to 1000, then you can see here the mean values are coming out to be 4.01, 3.8 to 4.0, and they are more close to the true theoretical mean 4. right. And similarly, the variance comes out to be 4.15, 3.60, 3.81, which is now more closer to here 4. But if you try to increase it more, that will become more closer to the true value. So, these types of observations you will be getting from such simulation experiments that you are trying to do here. So, these are the screenshots of the same outcome which I have just shown you. Okay, so now we come to an end to this lecture, and you can see that in this lecture that was pretty simple, exactly on the same line of what we did in the case of binomial distribution. We have used the R software to compute different types of probabilities from the Poisson distribution, but definitely it will be more helpful for you if you try to take some example and try to solve them yourself. Well, I will say once again that try to take very simple values, try to compute the probability manually, so that you understand the basic concepts, how the things are being done, and then you try to use them in the R software. That will give you more confidence that whatever software is doing, that is correct, and that is according to the rules that you know. And this will help you when you are trying to deal with much bigger data sizes, particularly when you are trying to work in the data sciences. You have to make automated program. Possibly these concepts and this confidence that you have gained with this smaller example, they will help you in becoming more assured that whatever you are thinking, that is being done, and whatever the outcome you are getting, you understand it. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.